So Jensen Huang, the CEO and founder of Nvidia, gave a presentation at the AI Summit in India.
Hello, Mumbai!
As someone who's kind of spearheading the AI movement, he's got a really good vision about where things are going. In his presentation, Huang shared a few interesting concepts that are going to be pivotal to how AI develops moving forward. Take a listen.
But we know now that the scaling of CPUs has reached its limit. We can't continue to ride that curve, that free ride. The free ride of Moore's Law has ended. We have to now do something different, or depreciation will end. And we now will not enjoy depreciation, but experience inflation, computing inflation. And that's exactly what's happening around the world. We no longer can afford to do nothing in software and expect that our computing experience will continue to improve, that costs will decrease, and continue to spread the benefits of IT and to benefit from solving greater and greater challenges. We started our company to accelerate software. Our vision was there are applications that would benefit from acceleration if we augmented general purpose computing. We take the workload that is very compute intensive and we offload it and we accelerate it using a model we call CUDA, a programming model that we invented called CUDA that made it possible for us to accelerate applications tremendously. That acceleration benefit has the same qualities as Moore's Law. For applications that were impossible or impractical to perform using general purpose computing, we have the benefits of accelerated computing to realize that capability. For example, computer graphics. Real-time computer graphics was made possible because of Nvidia coming into the world and make possible this new processor we call GPUs. The GPU was really the first accelerated computing architecture running CUDA, running computer graphics, a perfect example. We democratized computer graphics as we know it. 3D graphics is now literally everywhere. It could be used as a medium for almost any application. But we felt that long-term, accelerated computing could be far, far more impactful. And so over the last 30 years, we've been on a journey to accelerate one domain of application after another. The reason why this has taken so long is simply because of this. There is no such magical processor that can accelerate everything in the world. Because if you could do that, you would just call it a CPU. You need to reinvent the computing stack from the algorithms to the architecture underneath and connect it to applications on top. In one domain after another domain, computer graphics is the beginning, but we've taken this architecture, CUDA architecture, from one industry after another industry after another industry.
There was a bit of a slowdown effect on AI adoption because some of the software needed to be rewritten. He introduces this idea of software 2.0. The idea is that before humans wrote the algorithms, the code, everything was written out step by step. It was explicit instructions telling computers what to do. In contrast, software 2.0 is based on machine learning. Humans will no longer be writing the code. Take a listen to Huang talk about this phenomenon.
I think it's very, very clear now. The world has completely changed. Now let's think about what happened. The first thing that happened, of course, is how we do software. Our industry is underpinned by the method by which software is done. The way that software was done, call it software 1.0, programmers would code algorithms, we call functions, to run on a computer. And we would apply it to input information, to predict an output. Somebody would write Python or C or Fortran or Pascal or C++, code algorithms that run on a computer. You apply input to it, and output is produced. Very classically, the computer model that we understood quite well. And it, of course, created one of the largest industries in the world, right here in India, the production of software. Coding, programming became a whole industry. This all happened within our generation. However, that approach of developing software has been disrupted. It is now not coding, but machine learning. Using a computer to study the patterns and relationships of massive amounts of observed data to essentially learn from it the function that predicts it. And so we are essentially designing a universal function approximator using machines to learn the expected output that would produce such a function. And so going back and forth, this is software 1.0 with human coding to now software 2.0 using machine learning. Notice who is writing the software. The software is now written by the computer. And after you're done training the model, you inference the model. You then apply that function now as the input, that function, that large language model, that deep learning model, that computer vision model, speech understanding model, is now an input neural network that goes into the GPU that can now make a prediction given new input, unobserved input. This way of doing software, notice, is based on fundamentally machine learning. And we have gone from coding to machine learning, from developing software to creating artificial intelligence, and from software that prefers to run on CPUs to now neural networks that runs best on GPUs. This, at its core, is what happened to our industry in the last 10 years. We have now seen a complete reinvention of the computing stack. The whole technology stack has been reinvented. The hardware, the way that software is developed, and what software can do is now fundamentally different. A massive system designed to study data at an enormous scale so that we could discover patterns and relationships and learn the meaning of the data. This is the great breakthrough. In the last several years, we have now learned the representation or the meaning of words and numbers and images and pixels and videos, chemicals, proteins, amino acids, fluid patterns, particle physics. We have now learned the meaning of so many different types of data. We have learned to represent, how to represent information in so many different modalities. Not only have we learned the meaning of it, we can translate it to another modality. So one great example, of course, is translating English to Hindi. Translating English, large body of text, into other English, summarization. From pixels to image recognition. From words to pixels, image generation. From images, videos, to words, captioning. From words to proteins used for drug discovery. From words to chemicals, discovering new compounds. From amino acids to proteins, understanding the structure of proteins. These fundamental ideas, essentially a universal translator of information from any modality to another modality, has led to a Cambrian explosion of the number of startups in the world. They're applying the basic method I just described. If I could do this and that, what else can I do? If I can do that and this, what else can I do? The number of applications has clearly exploded. In the last couple, 2-3 years, the number of generative AI companies around the world, tens of thousands, tens of billions of dollars have been invested in this field, all because of this one instrument that made it possible for us to study data at enormous scales.
And finally, we start talking about AI agents. Jensen is very excited about the potential of these super employees, as he refers to them. To create these super employees, Jensen outlines the agent lifecycle, training AI with massive amounts of data to learn necessary skills, fine-tuning the agent's behavior to fit specific business needs, and then evaluating performance to ensure expectations are met. This includes establishing guardrails and safety protocols to ensure ethical and responsible operation. This process is going to mirror traditional employee training and onboarding, but will occur in the digital realm, which is where he mentions the next big thing that Nvidia has to offer.
So I'm going to introduce a couple of other ideas. And so earlier I told you that we have Blackwell, we have all of the libraries, acceleration libraries that we were talking about before, but on top there are two very important platforms we're working on. One of them is called Nvidia AI Enterprise, and the other is called Nvidia Omniverse, and I'll explain each one of them very quickly. First, Nvidia AI Enterprise. This is a time now where the large language models and the fundamental AI capabilities have reached a level of capabilities we're able to now create what is called agents. Large language models that understand the data that, of course, is being presented. It could be streaming data, it could be video data, language model data, it could be data of all kinds. The first stage is perception. The second is reasoning about, given its observations, what is the mission and what is the task it has to perform. In order to perform that task, the agent would break down that task into steps of other tasks. And it would reason about what it would take, and it would connect with other AI models. Some of them are good at, for example, understanding PDF. Maybe it's a model that understands how to generate images. Maybe it's a model that is able to retrieve information, AI semantic data from a proprietary database. So each one of these large language models are connected to the central reasoning large language model we call agent. And so these agents are able to perform all kinds of tasks. Some of them are maybe marketing agents, some of them are customer service agents, some of them are chip design agents. Nvidia has chip design agents all over our company helping us design chips. Maybe they're software engineering agents. Maybe they're able to do marketing campaigns, supply chain management. And so we're going to have agents that are helping our employees become super employees. These agents, or agentic AI models, augment all of our employees to supercharge them, make them more productive. Now, when you think about these agents, it's really the way you would bring these agents into your company is not unlike the way you would onboard someone who's a new employee. You have to give them training curriculum. You have to fine-tune them, teach them how to use, how to perform the skills, and understand the vocabulary of your company. You evaluate them, and so there are evaluation systems. And you might guardrail them. If you're an accounting agent, don't do marketing. If you're a marketing agent, don't report earnings at the end of the quarter, so on and so forth. And so each one of these agents are guardrailed. That entire process we put into essentially an agent lifecycle suite of libraries, and we call that NeMo. Our partners are working with us to integrate these libraries into their platforms so that they could enable agents to be created, onboarded, deployed, improved into a lifecycle of agents. And so this is what we call NVIDIA NeMo. We have, on the one hand, the libraries. On the other hand, what comes out of the output of it is an API inference microservice we call NIMS. Essentially, this is a factory that builds AIs. And NeMo is a suite of libraries that onboard and help you operate the AIs.
Now, of course, the next big thing after we sort of expand the digital world is the omniverse, right? There's the physical world, and when it comes to AI interacting with the physical world, Jensen introduces the concept of physical AI. So if you think about physical AI plus robots, that's the bridging of the gap between the digital and the physical. Nvidia has 3 types of computers for that sort of AI. We have the DGX systems for AI training, Omniverse as a platform for simulation and creating digital twins, and the Jetson AGX platform for deploying AI into the real world. Digital twins are virtual replicas of physical objects or environments, enabling AI to experiment and optimize processes in a virtual setting before implementing them physically. This approach allows for robots to train in performing complex tasks, testing new manufacturing layouts, and simulating disaster scenarios, all within a dynamic, physics-obeying digital environment. It's the real world simulated, with actual employees, with injuries, all the physics and all the complications of the real world.
What happens after agents? Now remember, every single company has employees, but most companies, the goal is to build something, to produce something, to make something. And those things that people make could be factories, it could be warehouses, it could be cars and planes and trains and ships and so on and so forth. All kinds of things. Computers and servers, the servers that Nvidia builds, it could be phones. Most companies in the largest of industries ultimately produces something. Sometimes production of service, which is the IT industry, but many of your customers are about producing something. That next generation of AI needs to understand the physical world. We call it physical AI. In order to create physical AI, we need 3 computers, and we created 3 computers to do so. The DGX computer, which Blackwell, for example, is a reference design, an architecture to create things like DGX computers for training the model. That model needs a place to be refined. It needs a place to learn. It needs the place to apply its physical capability, its robotics capability. We call that Omniverse, a virtual world that obeys the laws of physics, where robots can learn to be robots. And then when you're done with the training of it, that AI model could then run in the actual robotic system. That robotic system could be a car, it could be a robot, it could be an autonomous moving robot, it could be a picking arm, it could be an entire factory or an entire warehouse that's robotic. And that computer we call AGX, Jetson AGX, DGX for training, and then Omniverse for doing the digital twin.
And now the leap from digital twins to the physical world is going to be achieved through the Jetson platform, which is a smaller embedded system designed to run AI directly in robots and autonomous machines. This integration results in applications like self-driving cars, robots working in factories and warehouses, handling delicate tasks, and collaborating seamlessly with human workers. Once again, physical AI is not seen as a replacement for humans, but rather as a means to augment our human capabilities, making us more efficient and productive. Robots can handle the heavy lifting, the repetitive tasks, allowing humans to focus on quality control, problem solving, and specialized tasks that require ingenuity and dexterity.